Welcome to the 47th eBay Tech Talk. Enjoy the talk.
Yeah, thank you. Welcome from my side. It's a pleasure to be here today and talk about the topic deep learning for recommender systems and how we do that at mobile.de in order to improve our vehicle recommendations for our customers, for the people who search for the right car. Maybe some preliminary remarks. Who am I? My name is Marcel Kurovski. I'm a data scientist working for inovex, which is an IT project house based in different cities in Germany. I work in Cologne, and we are dealing with all sorts of helping our customers to digitally transform. In that case, we help mobile, and in this case, it's about recommender systems. This whole work was based on my master thesis, which I did last year. This master thesis was covering this specific part, but with the beneficial part that I could do it in practice at mobile.de, which I'm very grateful for. It was supervised by one of my colleagues, who's Dr. Florian Wilhelm, also a data scientist from inovex, and we both are part of the data team at mobile, working there for almost, I think, more than 2 years now, together on different data products. And today I will show you more about how we improve our recommender systems with deep learning. So that will be my agenda for today. First, I will give you some motivation, why we need or may need recommender systems, and how we can use deep learning in order to improve them. Then going over to some basics. So what are recommender systems in specific? I will not cover that much on the foundational deep learning parts today. I think in Berlin you can see that every day at 3 different locations, so I will rather focus on recommender systems. To then come to some other industry leaders who already implemented deep learning solutions for their recommender systems in different domains and show how they did that. To then come to the third point where I show you our approach and the results we got with that. And also give you some outlook on how it scales and which architecture we choose in order to bring that into production. Okay, so let's start with the motivation. So this is some chart which every one of you might have seen so far. Just describes what we already or everybody knows, that the data sphere globally is increasing exponentially. So data is some kind of everywhere, and with data, even though it is not data, but with data comes information. And we can safely also assume that the information that surrounds us also increases exponentially. And with that information, there are algorithms, machines that process this information, but also we as humans need to process information to come up with decisions and to decide and go forward. But where the information load increases exponentially, it's maybe not the case for us as humans regarding our capability to process them. So I would rather assume that due to the evolutionary constraints, this rather stays constant and does not increase with the same pace as the surrounding information does. So there's some kind of gap, a gap about information we need to proceed and our capability to proceed that information. And there may be a rather practical way of showing that. It's called the paradox or tyranny of choice. It's based on research from about 20 years ago, in which Iyengar and Lepper just faced customers, 2 groups of customers with different situations. In one situation, these customers were confronted with 20 sorts of different jam. And in the other case, it was just 6 different sorts of jam. And normally, I think we would assume the more, the better it is. The more choice there is, the better I feel, and the better I think my decisions are. But in fact, it was, at least based on how the conversions were, it was counterintuitive. Because the group with the 6 jams, they already got 10 times more people deciding to buy one of them as the group with a 4 times larger collection of gem. So we see we want to have a choice, but we also don't want to have too many choices. So more is sometimes less, so it is with choice. There was a book based on that research, The Paradox of Choice, and we tend to blame all of these as information overload. But there's some fundamental flaw. And this man, Clay Shirky, I think 10 years ago, he said something interesting. And he said, it's in fact not information overload, it's filter failure. So it's a totally different perspective of viewing the whole problem. It's not about becoming overwhelmed with information and getting into a passive position and saying, okay, I can't deal with that anymore, I can't decide, there's too much choice. It's about, okay, what about if we improve our filters to still benefit from the choice or from the information, but maybe in a different way. And when it comes to filters, or at least automatic filters, algorithms that filter information, these algorithms need to learn from something. And thus they pose a learning problem. And when we talk about learning problems, we have recently seen a large rise of a technology called deep learning, which is not that new at all. It has just perceived some rather lower phases. But now we see it in computer vision, we see it with autonomous driving, with speech recognition, where deep learning solves learning problems pretty well. One of the authors of my research in that context said, deep learning becomes a general purpose solution for nearly all learning problems. So it's not only a trend we see, it's delivering on that trend. Delivering with practical use cases and, for example, in skin cancer detection, where algorithms based on CNNs, convolutional neural networks, already perform on par or even better than top dermatologists, or even in other areas. So why not take something that appeared within the information age to address some problem or shortcoming that came with it? And this is how the circle kind of closes. So beginning with information overload, or what we would call it or perceive as information overload, we come to turning the problem into improving the filters, and then coming up with some kind of an implementation or technique that does this, and that are recommender systems. And these recommender systems at their core pose the problem of learning preferences and linking preferences of individuals to some sort of items. And then use deep learning to exactly execute this learning problem and therefore solve some kind of the information overload with deep learning. So I hope that gives some, even though rather theoretical, motivation, but at least every one of you, I think, might have already appeared these situations. So what does a recommender system exactly or in fact do? In recommender systems, we have generally 3 major parts that are, on the one hand, our users, that's you. On the other hand, that are our items. And we see that in different domains. Let's take, for example, Spotify. At Spotify, we have songs as the items. Of course, we have playlists, but the fundamental items are songs. And you, as the listeners, are the users. And then we perceive, and this is the third component, the interactions between both entities. We see people listening to music, we see people saving, bookmarking music, and so on. And the same it is with mobility. At mobility, we have a quite very large vehicle sales platform in Germany. And we have lots of cars. I think there are 1.6 million cars currently in the inventory available for customers. And we have even more consumers or customers, people that are looking for cars. And so we also see these interactions. So people that are clicking on cars, so viewing the ads, but also people that are contacting dealers or bookmarking, putting these items on their parking lot, bookmarking them. And how we call the third component, these interactions, is we denote it by implicit feedback. As you as a customer clicking some ad, do not do this in order to say us, hey, I'm interested. You do it because you're inherently interested, but not because you want to express this. So therefore it is implicit. If you go at Amazon and rate an item you recently bought, then this is called explicit preference, because the intention of your action is to explicate your degree of preference. And implicit preference, filling these matrices, is the most common thing we have, and is even much more implicit feedback as we have explicit feedback in recommender system settings. But now, for example, coming to the second user here, we are interested on what this user is doing in the future. What might he be interested in order to provide him with recommendations, what to do, what to see, and then to facilitate his decision-making process. So we like to fill these question marks. Those question marks with, for example, quantitative values, which we can take and then rank these cars on. So the first step might be a rather naive one, turning all the observed interactions into numbers, for example, ones. And then there are kind of two major fundamental methods towards solving this problem that are collaborative filtering and content-based filtering. For collaborative filtering, what we normally do is we look whether there are similarities between the actions of users. So, for example, taking our second user, we see he's pretty similar to the first user, even though there are just a few items here which is more for the visualization. But we see he's very similar to the first one. So it might be interesting, or it might be reasonable, to take the item the first user has already interacted with and take this as a recommendation for user 2, because he hasn't already seen this item. But due to the similarity to the first user, that might be pretty relevant for him. And we also can see users that are less similar, but maybe they will provide us with further information in order to improve these recommendations. So this is called collaborative filtering because it's based on what others did and what interactions others provided to then obtain similarities between those, taking these similarities to come up with recommendations. Another way of putting it, I think that's what was provided by Spotify. But a problem we normally face in these settings is called sparsity. So these matrices, given millions of users and millions of items, are generally pretty sparse. Just consider how large the inventory of Amazon is and how many items you clicked, bought, or just bookmarked on Amazon in your entire life. That might be a lot, but compared to the whole inventory of what you might interacted with, this is kind of nothing. And this is a large problem, but still also some kind of the characteristics of recommender system settings, that these matrices we have are pretty sparse. Therefore, and in order to solve this problem I illustrated before, the main algorithm to solve it we have is matrix factorization. So in matrix factorization, I tried to find lower dimensional matrices representing users and items to then use their product to reconstruct the original matrix. This allows me to have, for humans, non-interpretable representations for users and items, but representations that generalize well to new things, which I can then use to obtain, for example, the missing values in the matrix, order them, and have a notion about what might be the next relevant item for a user. But this doesn't solve it all, because especially in collaborative filtering, one major problem we are running into is the so-called cold start problem. So what am I going to do with users I have no information about yet? A user which did not interact with an item yet, because I can't estimate his similarity with another user if there is nothing to calculate that similarity upon. This is why another direction evolved. Maybe not it evolved due to that issue, but at least it solves that issue in a specific way, and that is content-based filtering. So between these two archetypes, collaborative and content-based filtering, we have content-based filtering, augmenting our items and users with features. In our vehicle case, that can be for the cars, the mileage of a car, or its model, its color, so different sorts of attributes from categorical or continuous domains. Or even other domains can also be Boolean ones, for example, if the car is used or not. And for the user, we can have the same attributes if we obtain them from previous interactions, or even user-specific attributes. Like, for example, the user's age, his gender, his income. And you may see there may be relations. So people with higher income may tend to buy other car models, or there might be cars that are preferred by younger people compared to cars that are preferred by older people. So these relations we can also exploit within matrix factorization and then come up with recommendations without needing explicit information on that very same user. At least no information on his interactions. So if this user in the content-based setting doesn't provide us with any interactions yet, we can still come up with recommendations for him using his attributes and the car attributes instead. But the problem about matrix factorization is that it's mostly linear. And as we live in a rather nonlinear world, it fails to capture the nonlinear underlyings. And even as we have seen some major advancements through deep learning, the question was quite evident, and the answer as well, so we need to go deeper. And this is what already some large players did. Some kind of a map I did, and what you can see at the top are different domains of recommender systems. So we already talked about entertainment, which I would see Spotify or Netflix in. You can also see e-commerce, social networks, or other domains. And we see different architectures of deep neural networks. So there are standard deep feed-forward neural networks, but also convolutional neural networks, mostly used in computer vision domains, or recurrent neural networks that capture the sequence of information, or autoencoders that get dense representations, but nonlinear representations, at least the deep autoencoders. And several large players tried several or different architectures. And I will just cover 3 of them, but it's pretty interesting, so if you're interested, look into more. Spotify, that was based on a nice blog post from 2014. What they did is they used a convolutional neural network with 4 convolutional layers. These are our convolutional layers you see here, and with 3 fully connected layers you see here, to get a 40-dimensional real-valued fingerprint of a song. So what they started with are so-called MEL spectrograms, meaning they used music of a song, cut it into 3-second pieces, and then they analyzed that music within each 3-second piece. And then you can draw some kind of a frequency distribution over time. And that is called a spectrogram. And this is some kind of a specific spectrogram. So it's some kind of a visualization of a song. And then they used this visualization with a neural network type designed for analyzing visual patterns, and then turning this visual representation of that song finally into that fingerprint. What they did afterwards is to see what does it bring us, and they could find, okay, we can even detect different kinds of music, and I know rock, pop, or classic, but they also found representations within a category of 100 that was that specific that it detected Chinese pop. So they went further with this, and at least as the author said, is that this is already or then went into production or as some kind of the part of the recommender system used at Spotify. So using these dense but nonlinear representations to capture information and then use these representations in order for the recommendation process. Like we have these representations coming out of matrix factorization, we can just use another model, but a rather sophisticated model, like this network I've shown before, to come up with other representations, but representations that are much more powerful. YouTube does something similar for video recommendations. So if you are watching clips on YouTube, you always see that right part here where you are displayed with the next videos, and normally I think they start with their first recommendation. And what I want to point out here is the architecture they used, or the higher level architecture, because this is something that is rather generic, and you see that in different implementations. And it's for that part, and also for my own approach, was interesting to see. So what we generally have in these domains is a two-step process. We are first creating candidates, and in a second step, we are ranking. And for both steps, they used a deep neural network. What are these steps about? As we are almost dealing with millions of items, and in the YouTube case with billions of users, we normally employ a first step of reducing that large corpus of videos to a few ones. For example, going from millions to just hundreds, like in this case. The same we do at Mobile, just with a different approach called Approximate Nearest Neighbor search. But this approach is based on our output from the networks I will show later on. And then, using this candidate generation, which is an algorithm that gives me, in a very fast fashion, things that are likely to be relevant for you, I then apply a computationally rather complex method to rank those items, and then to tell you, okay, these are the 10, 20, or so on most relevant items for you. And they also did this in a content-based fashion, not only using the interactions of users with the platform, but also the information they have about them. So you see that here, user history and context. So for example, which is the device the user uses to access the platform with, or what is his age, what is the time of the day, and especially also the tags of the videos, or the interaction history of the tags the user liked, and so on. Interesting was that they used a classification approach within the ranking network. So they finally make a classification and use the best classified ones as those to be recommended first. Finally, there's an approach which I started with, proposed by but by Google Play. They proposed wide and deep learning for recommender systems, and in that specific domain for app recommendations. So if you open your Google Play Store as an Android user, you may face the algorithms which are described in this paper. So they do something very similar. So based on a query, there's also some first retrieval step, reducing that large corpus of all available apps to a few hundred that are likely to be relevant for you, which are then ranked and then displayed according to the ranking within the app. And what they did is they did not only apply a deep neural network for their task, they used this deep neural network for a generalization. So they tried to capture some general concepts of what the user is searching for. They also used a wide component and, So they also used a wide component to capture specific combinations. So maybe specific combinations of an app you already installed and an app you are going to install, and then use these specific combinations to support the generalization. So they have generalization and this specialization, and then they combined these two, and that's why they called it wide and deep learning. And with that, they also obtained some higher conversion rates on the Google Play Store and were quite successful with that. So here in the neural network, you can also see that there's that deep component, just consisting of a 3-layer ReLU activated network. And then we also have that wide component, which is rather a linear combination of different features. And in before, you have some kind of embedding process that just reduces a large feature space to a more dense one, compressing the information and helping the deep component to then better generalize from that. So when we started with this, we were starting from that paper, also with a wide and deep learning approach, and having some adaptations to it regarding the cost function, but also regarding the specific domain we are dealing with, or also our candidate generation process. And finally, we went, I think, rather beyond the wide and deep learning approach and quite successful. So what was the fundamental structure behind this? So these are the steps I'm going to cover in the next minutes. So starting from the data we have on our users, so which user clicked which item, when, or contacted a dealer or something like that. Of course, we did some preliminary pre-processing on that data, and then we trained a classifier. A classifier whose fundamental task it is to distinguish between preference and disregard. Meaning for specific user item combinations, it should tell us, do they go together or do they not go together? And then employing some candidate generation process to reduce our large amount of items to a few relevant ones. Afterwards, using that very same classifier to then re-rank the candidates coming back from that process, and then serve them finally as recommendations back to the user. The technology we used for this, as we are mostly Python data scientists, was based on Google TensorFlow, which did not turn out to be that good for the preliminary exploration task or something like that. But at least in the end was quite a good choice, as with TensorFlow serving, we had a nice framework to bring things into production. I also used LightFM, which is a nice lightweight library for Python, having these standard recommender system algorithms on board, which helped us to get our benchmarks. For the candidate generation process, there are many libraries out there that do approximate nearest neighbor search. Here are just two of them. So one was proposed by Flickr, I think in 2014 or 2015. It's called locally optimized product quantization, and they use it at Flickr to search for similar images. So when you go at Flickr and you have some image, and then you have that option to search for similar images, this method is what's in behind, or at least what they claim which should be in behind. Eric Bernhardsen, who was, I think, some kind of the recommender systems expert for years at Spotify, came up with annoy, approximate nearest neighbor OER, which is the technique we currently use in order to come up with our candidates. Of course, we also used some additional libraries like every Python data scientist knows about, so there's nothing special about this. And we had luck to have some good computing processing power. So with an NVIDIA Tesla K80, it's nice to train deep networks on, especially when you have that much data. So coming to the data and what is interesting about it. The preliminary research was based on subscribed users. So subscribed users are users that have an account and normally log in, and the fundamental assumption was they provide us with even more, some richer information. They do not change that often. And from that set of our subscribed users, we selected a sample of 100,000. And we concentrated on 3 different events. So that are our view events. So if you click a car on the platform, that are our parking events. So saving them for later review or something like that. Or the contact events, when you contact the dealer in order to negotiate an appointment, or if you are really interested in a car and want to buy it or something like that. And within these users and items, we concentrated on different features. I think that are kind of the most important features we have, that are either continuous or categorical. So that is the consumption of a car, its first registration, whether it's used or not, the condition or its category, and of course the model or make ID we have. And what we did then is to apply a time-based train test split, meaning that we did that data collection process for 4 consecutive weeks. And on that weeks, we trained our algorithms and finally tested their performance on the last week, which was, in our case, the first week of May 2017. For that, we used weekly user profiles, which we generate based on users' past behavior, and use them to have some kind of artificial user features, as we don't have user original features or normally do not use them. So therefore, we kind of infer user profiles from their past behavior. So to have some kind of notion what might be the price a user is interested in, or the vehicles he likes, and the colors he likes or likes not. And also here, we saw the very same problem, because if you compare different research data sets in the domain of recommender systems, there's normally the movie lens, which is kind of the image net for recommender systems, or Last.fm, which is some kind of music recommendations, song recommendations data set. And our data set turned out to be even more sparse, with just considering the whole matrix of, I think we had in the end 1.7 million items, we had 8 million interactions. That first sounds a lot, but given the potentially or the possible interactions we can have, which is just 100,000 times 1.7 million, that means that out of 100,000 possible interactions, we see 5. So far to the sparsity. So it's a hard problem, but we will see how far we get with this. Of course, we did some pre-processing, so just some normal data fetching, some rehashing, the sampling. Rather interesting was, we call it content-related pre-processing, in which, as we train a classifier and we just have positive data, so observed interactions, we needed somehow to come up with negative data. Because if you want to train a classifier, you need labeled data and show him what's good and what's bad. And if you just have what's good, you can't train that classifier. So normally in recommender systems, this is a known issue. So users do not provide implicit or at least they do not provide implicit negative feedback that often. There might be possibilities, but it's rather rare. So the common case is that they provide us with positive feedback, and we need to artificially sample negative feedback from that, because we know what the user interacted with, and we know what he did not interact with. And for the two things he did not interact with, there are just two possibilities, because he did not know them, or because he did not like them. And from them, and from the user's positive ones, we can nevertheless sample negative examples, to then come up with the same amount of negative samples as we have as positive samples. What we then did was, of course, also some outlier removal and coming to the user profile conversion, which is rather interesting. Because as you already saw, I talked about user profiles, and this is a little fuzzy. But I want to explain that. Items are normally deterministic, meaning that for an item, we have at a specific time one single valid price, and the car has one valid color. So, and this is the case for our item storage. But as we do not use user-specific features, but the same features for the users as we have for the cars, we need to somehow infer from their interactions with cars what their features are regarding color, price, mileage, and so on. So therefore, in the case of continuous features, we can, for example, take the mean of the prices of the cars he interacted with and the standard deviation to have some kind of the notion what is the price range that user is interested in. For the categorical, the process is a little different. There we normally calculate a categorical probability distribution, taking into account the categorical values we are provided with. In that case, we have 2 black cars, 2 gray, and 1 red. And so we see, okay, 40% of the cars were red, and so on and so forth. And this is how we represent the very same features, which are normally car features, for a user. And then we can directly compare a user with an item, or even trade-off. So if the price, for example, of a car is higher than its mean, but the mileage is lower, that might give some trade-offs for the user and possibilities that then can be exploited by the network. So this is what we did in order to have these representations for users and for items. And now we want to say for a given representation, for user and item, is that good or is it bad? Is this item that was part of the input with that user a good one or a bad one? Therefore, we start with these representations we have, then having our 15 categorical features, where we do that, I call that one-many encoding for the user, so turning them into their categorical distributions. And for the item, we do a standard one-hot encoding, to then have a much larger space due to these encoding steps, resulting in 3,000 to 4,000 features, categorical features for a user and for an item representation. Those we can split into those that belong to each feature and then embed, meaning that we compress their information into a denser space and thus obtaining lower dimensional representations, but still trying to maintain most of the information that is contained there. For the continuous features, it's still a little more difficult for users, as we have that differentiation in mean and standard deviation. We can even use more, but we just reduce to these two. And for the car, of course, this is pretty simple. Then we use both continuous features for users and items to get continuous embeddings. And we do that within the same space. So for a user and for an item, based on his continuous features, I want to have a 6-dimensional, in that case, embedding to represent his continuous features. So it's just 6 real values that are not anymore interpretable for us, but interpretable at least for the network. These are concatenated with the categorical embeddings, meaning that we just bring them together, and thus we have some kind of vectors of size 70, 80, or 90. So much lower as at 3,000 to 4,000 dimensions. Much more handy, but with a dense information. These embeddings are kind of the centerpiece of our approach, as we use them not only for the network here when we train the classifier, we use them for the ranking, and we use them for the candidate generation. First step, and this is now tell us for these embeddings, for that combination, we just use a standard deep feed-forward neural network with an exponential linear unit activation here, where we put into these representations for items and users, and then apply a sigmoid activation, which we then can interpret as a probability that the user interacts with the item. And that probability we can then use to rank upon. So for example, taking a specific user and 10 different items, I obtain 10 different probability estimates, and then can use these probability estimates to rank the list of items. So what we then did is to show that network our 16 million data points, train it to excel at that classification task, and then use the trained network after the convergence in order to do that later on in the recommendation process. So therefore, we isolated after training the so-called usernet and itemnet. So it's pretty much the weights we use to turn user raw features into the user embedding. So what we did here, is just how do we come from the user's raw representation to the embedding, and then we isolate that network, the same we do for the item net, and we also isolate the rank net. So we have 3 components, which are then relevant for our final architecture. In a rather simple way, this looks like that. So what we also did is using 2 different losses. Of course, as we like to solve a classification task, there's a classification loss that quantifies how good I am at, or how bad I am at classification. And then we use an Adam optimizer, stochastic gradient descent, in order to minimize that error and adapt the weights within that network in order to minimize this error. We did some addition, which we haven't seen so far in the papers we used, and that was using a separate optimization for the user and item net training. And this was based on the idea that went beyond that normal loss function. This is the standard cross-entropy loss function, which normally just tells you how good I am at classifying. But it was not only our concern to be good at classifying, it was also our concern to be good at coming up with dense user and item representations. And therefore, we added a regularization term in which we used for users and items their raw representations, calculated how similar they are using the cosine similarity, And then we asked, okay, how similar are these two based on their embeddings? To then calculate the difference and make the network minimizing this difference. Maybe I will give you some rather geometrical notion of that. So if you have a large dimensional space, let's say 3, then we may have a user and an item which I can represent as a vector in that space. And these two vectors span an angle. This angle can or just serves as a proxy for similarity. The larger it is, going to 180 degrees, the more dissimilar they are. But if that angle becomes close, they are pretty similar. Okay? What we did through our network is to compress the dimensionality. So we went from these 3 to 4,000 to a space of just 70 or 80. Or in that case, from 3 to 2. But what we still want is that there is no distortion of the similarity, that the similarity is maintained. So by embedding and by reducing that space, I don't want this user and item representation to become close suddenly or become even further apart. I want them to still have the same angle and to still be dissimilar in the way they were before. So, and this is the notion behind that addition in the loss function we applied and which we guided the network to respect during training. And we need this to have embeddings for users and items that are finally comparable. We cannot guarantee that they are comparable yet, but at least forcing them to maintain their similarity throughout the embedding process, we try to keep their comparability. And why do we need this? Why do we need a user being comparable with an item? And we can't assume that from the very beginning, because as I said, items have other representations, deterministic ones, as users have. Therefore, we didn't assume to have them, that comparability, and tried to enforce this. We need this for our candidate generation. Because if we want to find nearest neighbors, items that are likely to be similar to a user, we need to find them fast. And for example, here in a two-dimensional space, where that mark in the middle of the circle here might represent a user, we like to find his 5, 10, or 200 nearest neighbors pretty fast, to then rank these nearest neighbors using our ranking network. And therefore, we needed to come up with representations, with these embeddings, which we can put into the same space, users and items, regardless of these two being two different things. And this is what we do within Approximate Nearest Neighbor search. We take a specific user, his 70 or 80 dimensional representation, just a collection of real values, and then take that as a search query within our Approximate Nearest Neighbor search method, which then returns us the T, maybe 100 or 200 nearest neighbors of that very same user. In that case, you see, it's not always the really nearest neighbors, it's the approximate ones, because we do some slicing techniques within that space in order to speed it up, but still make these candidates returned to be relevant. So there's some kind of trade-off. I want to do it fast, and therefore I'm willing to give up some of the quality of the precision I have there. So what we used was that approach from Spotify, which is called annoy, to target or to reduce our 1.5 million vehicles we have to, for example, 100 or 200 in milliseconds. So when I did that reduction for a specific user, I have a next task, and that is, of course, to take these approximate nearest neighbors and rank them. And there is some component I mentioned before we can now reuse, and that is our RankNet. So we take the very same user now, and we take the candidates, push them through the RankNet, reorder them, and then we have a ranked list of the best candidates, which we can then use to display them to the user in the next step as his recommendations. So far, the approach we have taken, and now also the results. There's some preliminary remark. The left scale looks quite low, but based on the restrictions we applied, we at least think it's far more higher regarding the relevance. But what matters more in this context is the comparison between the different methods we had. So we applied some basic methods. So we first used collaborative filtering, as I mentioned before, which as expected was performing pretty low. In the next phase, we used matrix factorization using content-based filtering and collaborative filtering. So not only using the interaction signals, but also the features, but still in a linear fashion because of matrix factorization. So this is the second one. As expected, it's better because the difference between these two now is that here we also used the content information. So mileage, model, and so on. With deep learning, we were able to obtain that. And within the very specific domain of k equal to 5, so if we like to put out 5 recommendations, which is mostly the use case on our platform, this allowed us to improve the results by 73 to 143%. And as we assume that the current recommender is somewhere in between these two, it just means that we were able to double the relevance of recommendations using deep learning. So this is what we did, and yeah, we were quite lucky with the results, or not lucky, we were happy about them. And then, of course, the next question was, how do we bring this to the customer, to the end user? So what then arose was rather fast the concerns about how well does that scale and how do we bring this into production. And there we came up with the following architecture. So we have our user profile API that kind of generates these user profiles for our users. And then we have some kind of an orchestration framework implemented in Scala right now. So, and what we did is these 3 networks I mentioned, which we already isolated, we brought them into Docker containers using TensorFlow serving, which is the proprietary engine of TensorFlow to bring these models into production, make them queryable. And what a user now does is he's facing this recommendation service that in its core has 2 sub-services, which is the ranking and the candidate service. Meaning that when there is a customer who is navigating through the platform and thus creating a request for recommendations, we try to fetch his profile, push his profile through our usernet to obtain that embedding. Then we use that embedding to go against our candidate service to then get the, for example, T best candidates. And then what we do is just take this embedding of the user we already have in memory and rank it against these T candidate embeddings we have here to then select, for example, the 5 best and push them back as recommendations. And within the candidate service, we have our item storage, which is basically all the vehicles that are currently active, and a job that is then regularly running which turns first these items, their raw representations, using the item net into embeddings. And then we have the annoy index training, where these embeddings are specifically indexed in order to allow fast search, approximate nearest neighbor search on them, and then to do that in a time window of tens to 100 milliseconds, to then also perform these recommendations quite fast. So, as I said, we were finally quite happy to have chosen TensorFlow, because TensorFlow might be a little bit difficult in the beginning to begin with, and if you do, for example, some more exploratory things or something like that, I would rather recommend using PyTorch. But when it turned to the trained model and the question to how do we bring that into production, we saw that with TensorFlow serving and the engine and Google's proprietary remote procedure call protocol, it was quite easy to do that. So you can just deploy that whole thing in a Docker container, horizontally scale it, and if you like, put it into some kind of cloud environment. So finally, we have seen that using deep learning, we are much more flexible as within the traditional solutions, because adding that, what I've shown here, for example, maintaining the similarity between embeddings was quite easy. It was just an adjustment of the cost function. It allows us to have a better abstraction from these representations we deal with. Representation that is not only based on linear signals like in matrix factorization, but also on nonlinear interactions. And it still allows for the hybrid context in which we incorporate collaborative signals, content-based signals, but we might also incorporate further signals like context signals. So at which time am I providing recommendations, or some other user-specific environment variables or something like that. So therefore we are finally pretty happy having gone into that direction, and I'm also quite happy to talk about this and hope that you got some glimpse into deep learning for recommender systems. Thank you.
So how often do you need to retrain your networks in a production environment?
Good question. I can't answer it right now. Because the prototype is currently finished, but we are still on the point of starting with A/B tests, so I don't know that now, so sorry.
So, but is this a continuous process? Or is this necessary, I don't know, once a year after the EIA automotive exhibition or something like that?
So what I have seen from research is that normally the quality of a trained recommender system degrades by time. So therefore, of course, we assume that we need to retrain it by some time, and I estimate it would be somewhere between weeks or at maximum, I think, a month. But you will have to retrain it in order to avoid that that performance or quality performance drop.
Thanks for the presentation. So I'm not an expert in the car selling domain, but I have an impression that users usually come once in a year, or maybe quite rare. So actually, this is the reason why you have so sparse data. And one of the solutions for such cases is just to model user information as the combination of the items with which user interacted. So for example, like aggregation of item embeddings. So did you try something similar? Did you check the results? Did you compare?
We did not combine item embeddings for past interactions, but we did this in a more prior step. So I think we did this because coming up with that user representations requires us to look into his interaction history and then to look into the cars that are linked to these events and takes their information. This was when I showed the slide about the user profiles. So then we take into account, for example, the 5 prices of these cars, which then gives us an estimate for the user price. So the price the user is looking for. So we already do this in a way, but more as a prior step, coming up with the raw data.
In this case, it looks like user is just separate embedding, but it can be just averaged of the item embeddings. And it also simplifies the KNN search, the nearest neighbor search for item selection.
Okay,
so
maybe
it will reduce the amount of
no, that's an interesting point. So one could try that. So you would mean you would not take the user raw representation, but rather, for example, the embeddings of the 10 cars he interacted with, and then average them, or for example, take the average, max, min model and display them to the network.
Yep.
Yeah. Okay. No, we didn't try that.
Second question: could you explain more what type of hybrid solution did you use for comparison? So you had some baseline models, and you mentioned the hybrid model. What was the hybrid model?
The hybrid model was just matrix factorization, but factorizing these features we have and also the collaborative signals. So we have the collaborative filtering, and then it was just taking the features of items and users on top, which then brought us to the hybrid CF-CBF approach, but still in a linear fashion.
You said you are happy with the results of your recommendations. How do you know, or how do you measure if your recommendations are very good?
So that's a good point. The current results are based on an offline evaluation. And that's always some kind of a problem in these settings, because offline evaluation is just one part. The offline evaluation was that good that we decided to go forward with this and to get a prototype, which we then can also online test. So to answer that, and that's the next question, the next step is of course to do online testing, where we would do some standard A/B testing, displaying some users with an old recommender, some other users with a new recommender, and then see how the conversion rates behave for different recommender settings. So this is just one one part of the overall evaluation. But within that one part, within that offline evaluation, I think we took kind of a really established way to evaluate it, because mostly you use the mean average precision at k. And I did not cover that in detail. So mean average precision just normally says if you have one user and you know what he actually interacted with and you know what you predicted him to interact with, you can see how many of those turned into true ones which he interacted with, and then you take for k positions. So if you are able to make 5 recommendations and you look into that 5 interactions of the user, how many did you hit? And then you average that factor across all users, and this is how you come up with the mean average precision, which we used for our offline evaluation.
Okay, well, if that's the case, I'd like to take the opportunity to point out that those of you that are here that'd like to know more about this, if you're interested in reading a little bit about this, Marcel has published an article on our blog at ebaytech.berlin. So if you visit ebaytech.berlin, you can read a lot about what Marcel spoke about tonight in case you missed any of it. So that's a place to follow up.
And there's some gimmicks, so at the end of the blog post you will also find the link to the whole academic work, so if you are really interested or want to see the references, have a look there. Thank you.